Welcome to all in the lecture series of functional analysis. Now in this lecture we see the theorem about the algebraic dual space X star of the vector space X, and the statement is let capital X be an n-dimensional vector space and capital E be the set of all E1, E2 up to so and En a basis for capital X. Then capital F equals to the set of all F1, F2 up to so and Fn given by Fk of Ej equals to delta Jk, that is equals to 1 if J equals to K and it is equals to 0 if J not equals to K, is a basis for the algebraic dual space X star of X, and dimension of X star, it is equals to dimension of X equals to n. That is we have to show. Now here given that the set capital F is a base for the X star, that means here we have to show that the set capital F is linearly independent and every element of X star has a unique representation in terms of F1, F2 up to so and Fn. Consider summation k is from 1 to n beta k Fk of X equals to 0, where for any small x belongs to capital X, small x be any element of capital X. Now here we consider the summation of beta k Fk of X equals to 0. Now we have to show that as this sum equals to 0, then we have to show that for each k beta k equals to 0, that is we have to show. Then we get that the set Fk, it is a linearly independent set. So here as this equality is true for any x belongs to capital X, and here E1, E2 up to so and En, it is a basis for capital X, that means each Ei is the element of capital X. So we can take the value of X equals to Ej, where J be any fixed element. Okay, then for this X equals to Ej, here we are getting summation k is from 1 to n beta k Fk of, now instead of X we are writing Ej, Fk of Ej equals to 0, but Fk of Ej, it is nothing but delta Kj, and delta Kj equals to 1 for J equals to K, and that is equals to 0 for J not equals to K. That means in this sum here we have beta 1 F1 of Ej plus beta 2 F2 of Ej up to so and something. Here we have beta j Fj of Ej plus beta j plus 1 Fj plus 1 of Ej plus, and the last term is beta n Fn of Ej equals to 0. Now here F1 of Ej, it is nothing but delta 1j, it is equals to 0, F1 of Ej, this term it is equals to 0, and here we are getting beta 1 into 0 plus here again F2 of Ej, F2 of Ej means delta 2j, and it is equals to 0 because j not equals to 2, and therefore here we have beta 2 into 0 up to so and plus, now here beta j and here Fj of Ej, that means j equals to k, and therefore here we have delta jj, and delta jj it is always equals to 1, and therefore beta j into 1, and all the terms are again equals to 0, and therefore here we are getting that this implies that beta j equals to 0, but here we are considering j be the fix. That means for x equals to Ej, we are getting that beta j equals to 0, and as we are taking j be the fix, that means here it is true for each j beta j equals to 0. That means here we say that is for each fixed j, x equals to Ej implies that what we are getting here, beta j equals to 0, and therefore thus summation k is from 1 to n beta k fk of x equals to 0 implies that all beta j's are 0, and as all beta j's are 0, it implies that the set containing the elements f1, f2 up to so and fn is linearly independent, and hence we prove the first condition for the basis that the set f containing f1, f2 up to so and fn, it is a linearly independent set of vectors. Now after that, here we have to show that it is a basis for x star. That means we have to show that now we have to show that every element of x star has a unique representation in terms of f1, f2 up to so and fn. That is we have to show. That means here we have to show that every element of x star has a unique representation in terms of f1, f2 up to so and fn. That is we have to show. Now for this, here we start with any arbitrary element of x. We start with let small x belongs to capital X with the arbitrary element, or it is the vector with the arbitrary element of x, and the basis for x is n, capital E, with the set containing E1, E2 up to so and En, with the basis for capital X. And therefore, as it is the basis for capital X, therefore this small x has a unique representation in terms of E1, E2 up to so and En, and therefore we write down, therefore small x has a unique representation x equals to the summation, we are writing here j equals to 1 to n xi j ej. That is the unique representation of x. Now we give it the equation number 1. Therefore for f belongs to x star. Now here we are starting with the element of x star. Therefore, for f belongs to x star, be any arbitrary element of x star, we get f of x equals to the summation j is from 1 to n xi j into f of ej. We are writing this directly because here, as f is any element of x star and x star be the set of all linear functionals on x, and therefore f is also linear. Due to this linearity of f, we can write down it is equals to the summation over j xi j f of ej. Now we write down for this f of ej as alpha j, and that is equals to the summation j is running from 1 to n xi j into alpha j, where alpha j equals to f of ej for each j, and j is between 1 to n. This is the value of f of x. We give it the equation number 2. Now also for each j f j of x it is equals to, now we are putting the value of x, fj of, the value of x is xi1 e1 plus xi2 e2 up to so on something here, xij ej up to so on plus xi n en. Now fj is a linear functional and therefore we can write it as xi1 fj of e1 plus xi2 fj of e2 up to so on. Here we have xij fj of ej up to so on xi n fj of en. Now here we know that fj of e1, that is the delta j1, and as j not equals to 1, therefore it is equals to 0, and therefore this term whole becomes equals to 0. In the same way, j not equals to 2, therefore fj of e2, that is equals to 0, and therefore the product xi2 into 0, that is also equals to 0. This is continue, but here fj of ej, that is equals to delta jj, and delta jj equals to 1. Therefore we get here the product xi j into 1, that is equals to xi j plus, and all the remaining terms are 0. That means it is equals to xi j. That means here we get that fj of x equals to xi j for each fixed j. For each fixed j, and j is between 1 less than or equals to j less than or equals to n. In this way we get the value of xi j, that is equals to fj of x. Now here we give it the equation number 3. Now we combine the equation 2 and 3. We get from equation 2 and 3 we get f of x, that is equals to the summation j is from 1 to n. We write down the value of xi j, that is the value of xi j is, we are getting that value fj of x into alpha j, and therefore it is equals to summation j is running from 1 to n alpha j into fj of x. It is true for every x belongs to capital X. Therefore here we get that we get f of x equals to the summation for every x belongs to capital X. F of x is written in the terms of summation j is running from 1 to n alpha j fj of x, and it is true for all x belongs to capital X. It implies that this small f has a unique representation in terms of fj, and therefore here we say that the unique representation of the arbitrary linear functional f, because here we are taking f belongs to x star, be any arbitrary element of x star, and this arbitrary element of x star has a unique representation on capital X, as f belongs to x star be arbitrary. It means that we get every element of x star has a unique representation in terms of the functional f1, f2 up to so on fn, and hence that representation is written in the form of f equals to alpha 1 f1 plus alpha 2 f2 up to so on plus alpha n fn, and therefore every element of x star has a unique representation in terms of f1, f2 up to so on fn, and this implies that the set capital F of all the linear functional f1, f2 up to so on fn, it is linearly independent, and every element of x star is written has a unique representation in terms of f1, f2 up to so on fn, and therefore the set F is a basis for x star. X star is the algebraic dual space of x, and therefore as it is a basis for x star implies that dimension of x star, that is equals to n, but n is nothing but the dimension of x. That means here we get that the dimension of x star equals to the dimension of x. But it is true only when x is finite dimensional. That means here we get that dimension of x star that is equals to dimension of x that is equals to n. That means if capital X is finite dimensional, then its algebraic dual space, its dimension that is also equals to the dimension of x. But here as x is finite dimensional, then here we get the dimension of x that is also finite. That means here we get that x star is finite dimensional. X star is finite dimensional. But as x star is finite dimensional, again we are using the same theorem. As x star is finite dimensional, therefore its algebraic dual space, that means star of x star, is also finite dimensional. Is also finite dimensional. And here in this theorem, here we get that if x is finite dimensional, then we are getting that the dimension of its algebraic dual space, it is equals to the dimension of x. In the same way, same theorem applying for x star, here we get that as x, here we are getting that x star is finite dimensional, therefore its algebraic dual space, that means the star of x star, that is also finite dimensional, and dimension of star of x star, that is the dimension of second algebraic dual space, it is equals to the dimension of algebraic dual space. But dimension of algebraic dual space, that is equals to the dimension of x, and it is equals to n, which is strictly less than infinity. That means if x is finite dimensional, then the dimension of its algebraic dual space as well as the dimension of second algebraic dual space are all same, and they are also finite dimensional. This is the proof of the theorem about the dimension of x star. Now after this theorem, we see the lemma about the zero vector. The statement of the lemma is, let capital X be a finite dimensional vector space if x naught belongs to capital X has the property that for every f belongs to x star, its image, that is f of x naught, equals to 0, then x naught equals to 0. That means for any element of x star, its image equals to 0, then the element, then the vector must be equals to 0. This is the lemma. Now in the proof, here we have to given that capital X be a finite dimensional vector space. As capital X is finite dimensional vector space, that is dimension of x equals to n. Therefore, it has a basis, and let the set containing E1, E2 up to so on En be a basis for capital X. As it is a basis for capital X, then x naught belongs to capital X has a unique representation x naught equals to xi 01 E1 plus xi 02 E2 up to so n plus xi 0n En. It is written in the form of summation is, that is x naught equals to summation j is running from 1 to n xi 0j ej. It is the value of x naught. Now here let f belongs to x star be any arbitrary element, be arbitrary, it is any arbitrary element of x star. As it is the any arbitrary element of x star, therefore be arbitrary element, then f of x naught, as f belongs to x star be any arbitrary element and x star be the set of all linear functionals on x, and therefore f is a linear functional on x, and therefore here f of x naught by f of x naught, it is equals to f of this summation j is from 1 to n xi 0j ej. But as f is linear, therefore it is equals to the summation j is from 1 to n xi 0j into f of ej. But we are writing f of ej equals to alpha j, and therefore it is equals to f of x naught, it is equals to summation j is running from 1 to n xi 0j alpha j, where alpha j equals to f of ej for each j, for each j 1 less than or equals to j less than or equals to n. Now here we are getting the value of f of x naught in terms of xi 0j alpha j, that is f of x naught, it is equals to the summation j is from 1 to n xi 0j alpha j, where alpha j equals to f of ej for all j, and j is between 1 to n. From this here, but we have to given that f of x naught equals to 0 for every f belongs to x star. By assumption f of x naught equals to 0 for all f belongs to x star, and therefore as f of x naught equals to 0, but here we have the value of f of x naught equals to this summation, therefore f of x naught, that is equals to the summation j is from 1 to n xi 0j alpha j equals to 0, and it is true for all f belongs to x star. As it is true for all f belongs to x star, and here f alpha j, it is equals to f of ej for each j. This is true for every element of x star, that means it is true for every alpha j. That means here for every choice of the scalars alpha 1, alpha 2 up to so n alpha n, we are getting f of x naught equals to 0. We are getting for every choice of scalars alpha 1, alpha 2 up to so n alpha n, we get that the summation xi 0j alpha j equals to 0. As it is true for every choice of scalar alpha j, this summation equals to 0. It implies that xi 0j equals to 0 for all j, and therefore here we get that xi 01 comma xi 02 and so on up to so on xi 0n are all 0, but as they are all 0, and here we know that x, therefore x is written in the form of xi 01, xi 02 and so on, and therefore here we say that therefore x, that is equals to xi 01 e1 plus xi 02 e2 up to so n plus xi 0n en. But here the value of xi 01, it is equals to 0, therefore this product equals to 0. Xi 02, it is equals to 0, therefore this product equals to 0 up to so n this product equals to 0, and here we get that this is the x naught, therefore here we get that x naught equals to 0, And in this way we show that if x naught belongs to capital X has the property that f of x naught equals to 0, for every f belongs to x star we get that x naught it is equals to 0, and hence the proof of this lemma.